Okay, so hi there everyone. We're now in our next video in college algebra, and in this video we're going to talk about more about radicals. And here we have just finished our video in the law of radicals and the radicals as an introduction. Here we're going to have this lesson in principles of simplifying radicals. This is much important, very much important when we before we go to the operations on radicals and how to simplify radical or expressions with radicals. So we have 5 principles, and in each principle, we're going to present at least 2 examples per principle. Okay. So first principle is what we're going to do is to remove the radical form, okay, the radicand form rather, or rather remove the radicand from. Okay, sorry, remove the radicand from the radical sign as much as possible or whenever possible. So if we just can remove the radicand from the radical sign, so it's going to make our work much cleaner, and the confusions will be somehow deleted. So again, as much as possible, we will be um, getting away with the radicals. So for instance, we have 3 examples here. The first example is square root of 196. So if you want to check, square root of 196 is equal to 14. Why is that true? Because 14 times 14 is going to give us 196. That's 1 times 4 plus 1 times 4 is going to give us um, 8, and then it becomes 16. So we have 1 plus 8 plus 1, so that's going to become 196. Okay, 196. So that's for number 1a. For number 2a, we have cube root of 64. So what number? If we can, if you can just remove the radicand, so much better. So what number multiplied by itself 3 times is going to give us 64. Okay, what number is that? So if you're just going to check, that's going to give us 4. Again, why is that 4? 4 times 4 is 16, right? So 16. Add another 4 there, multiply it to another 4. So we have 16 times 4, which is 4. 6 times 4 is 24. That's going to give us pretty much, I cannot put it there, that's going to give us 64. Okay, which is the answer, the one written here. For letter C, we have the fourth root of 256. So for the fourth root of 246, you just need to check what number will be multiplied by itself 4 times, which and will give us 256. So what number is that? Um, just try a little bit on yourselves, but you can see that eventually it's gonna give us 4. So meaning we're going to multiply 4 by itself 4 times. So that's 4 times 4 times 4 times 4. So therefore, this is 16 times 16. Okay, 4 times 4 is 16. 4 times 4 is 16. So let's try 16 times 16. What will be the answer? 1. 6 times 6 is 12. Um, 6 times 6 is 36. So so we have 256, which is the answer here. So therefore, thus the fourth root of 256 is equal to 4. Okay, so the answer for number 1 is 14. Number 2 is 4. Number 3 is also 4. Okay, so for that's for number 1. For number 2, what we will do is to make the radicand as small as possible. So in whatever we do, we must make the radicand as small as possible. Looking at big radicands will be quite dangerous when we just keep on doing that continuously, because we don't know, maybe we can simplify the radicand and combine it with another term. Um, we don't know that because we just didn't simplify or make the radicand as small as possible as we can. That may give us, if we will not be simplifying radicals, that will tend to give us a long expression in which in fact it is short, and we can combine some. Okay, so for instance, for square root of 8, so this is automatically, there's a 2 there as an index. So what's square root of 8? Obviously we cannot do square root of 8, but we can factor the 4, or we can factor the 8 rather, in which one of the factors is a perfect square. What the fact One factor is actually 4, so that's 4 times 2. So we can actually distribute the square root symbol in a say in such a way that it looks like this. And then square root of 4 is 2. So therefore, that's 2, and we cannot do anything with square root of 2. So that's our answer for letter A, 2 square root of 2. So for letter B, we have the cube root of 54. If you want, you can try that out for yourself. The same with the fourth root of 80. Okay, so maybe you can think of a number which is a factor of 54, and that's a perfect cube. So eventually you will see that that number is actually 27. 27 times 3, or times 2 rather, times 2, not 3. Okay, so 27 times 2. So we know the cube root of 27 is equal to 3. We can also do it like this, so that becomes the cube root of 27 as one of the laws in radicals. The cube root of 27 times the cube root of 2. Cube root of 2. So the cube root of 27, we know that as 3. So the cube root of 27 is 3 times the cube root of 2, in which we cannot simplify, obviously. So that's our answer for letter B. That's our answer for letter B. Cube should be a cube root. Okay. So for letter C, we are asked the fourth root of 80. Again, we need to find some number in which one of the perfect fourth roots, which is a factor of 80, can be taken from 80. So what perfect fourth root is that? Actually, the perfect fourth root for that is 16. It's gonna give us 16. Fourth root of 80 is equal to 16 times 5. Since 16 times 10 is 160 divided by 2, that's gonna give us 5. So therefore, that's gonna give us 80. 16 uh, times 5 is 80. And 16, the fourth root of 16 is what number will you multiply by itself 4 times will give you 16. That's going to be 2, right? So 2 times 2 times 2 times 2 is going to give us 16. Okay, so this is 2 times 2 is 4. 4 times 2 times 2 is 4. So we have 4 times 4. Obviously, another is equal to 16. Okay, so we know that again this can be distributed. This becomes fourth root of 16 times the fourth root of 5. So this becomes the fourth root of 16 is equal to 2, while the fourth root of 5 cannot be taken out of the radical form. So we'll just write it there as normal as it is, or we can just delete the the raised bar, okay, entirely. That will give us 2 to the fourth root of 5. That's 2 to the fourth root of 5. As you can see, these things, even though it's quite tasky to get them, but it's much better to look at cube root of 54, though it's a big number, but who knows, maybe you can combine cube root of 2 with another term. So if it's just going to stick with the cube root of 54, it's going to be another addends. It's going to be another addends, other than it can be simplified actually. So that's also all true for the fourth root of 80. Um, One thing to keep in mind here is that you should also be good with your multiplication table, in order, and also some familiarity in squaring and cubing numbers, because without one, this will be quite tasky for you, especially here. For the 54, we know that a factor of 54 is 27, in which it's a perfect cube, so we can do the extraction from the cube root of, I mean, the cube root of 27 will become 3. Likewise here, the fourth root of 16 is equal to 2, because 2 um, multiplied by itself 4 times is going to give us 16. So we just need to have some familiarity about those things, so that we won't get, so that the computations will be faster, okay, and it will be done in a matter of seconds rather than minutes. Okay, let's continue with the third and fourth principles in simplifying radicals. So, number 3, make the order of the radical as low as possible. Not only the value of the radicand is small, but also make the order as small as we can. Actually, 2 and 3 can be used must be used, okay, so that we can simplify all radicals in a given expression um, much more. Okay, we can simplify it much more. So for instance, we have the sixth root of 8 um, using one law of radicals that we have learned in the previous video. So what we can do is this can be equal to, so the sixth root, we know that 8 is a perfect cube, right? 8 is a perfect cube. So what we're going to do is to make sure that this becomes a cube root of 8, and we're going to add another index for that, and this will be a 2, since 2 times 3 is going to give us 6. So we must erase the 2 there, okay, even though there's a hidden 2 there. So 2 times 3 is going to give us 6. So in that matter, um, this is how it is done. So we have the square root of the cube root of 8. Again, the square root of the cube root of 8. We know that the cube root of 8 is equal to 2. So therefore, our answer here is going to be this thing will be entirely be deleted, and it will all become 2. So therefore, but we are left with the bigger square root symbol, right? So we didn't touch that. So therefore, the answer here is square root of 2. Okay, so for the letter B, we have the sixth root of 49. The sixth root of 49. So we want also to simplify this, and one can see that 49 is a perfect square. So we just need to put that on a square root, and then um, just make the other, this time the cube root, outside. So with this, we know that the square root of 49 is 7. So we are left with the cube root of 7, and that's our answer for letter B here. And for letter C, we have the sixth root of 100. Again, 100 we know of as a perfect square. So similarly with letter B, we will make it like it's going to become square root of 100, square root of 100, and the cube root of, on a on, under a cube root. So what we have is a cube root of the square root of 100. We know the square root of 100 is equal to 10. So we are left with the answer, which is the cube root of 10, which is the last step for for letter C. For number 4, this is also very important. There should be no rational radicand. So if the radicand is a fraction, so I mean rational as a fraction, specifically a fraction, whole numbers can be rationals, right? Also called rationals in short. So when I say rational, I mean fraction. There should be no fractional radicand, because you will know that in the in the fifth rule, or the fifth principle, that there should be no radical sign in the denominator of a radical rational expression. So there should be no square root or cube root or anything. So with this, let's make it a solve for this. We have the square root of 1/3. We cannot do that because it will give us square root of 1 over square root of 3 here. So aligned with the number 5 principle, let's just simplify this first. Square root of 1 is 1, because 1 times 1 is 1, but we have square root of 3 here. So we cannot do this. What we will do is what we're going to call this rationalization. So rationalization. This is the process, rationalizing, or simply rationalize it. This is the process wherein we need to get rid of the radical sign in the denominator part. Okay, we need to get rid of the um, radical denominator, which cannot be. Okay, we only use rationalization if it's a single term in the denominator that we need to cancel. If it's a binomial, we call that a conjugate. Okay, so how can we cancel square root of 3? So simply by rationalizing, we're going to multiply that by 1. And we want the style of 1 to be square root of 3 all over square root of 3. Right? This is equal to 1 because they're the same. So we're canceling them. It's going to become equal to 1. So we're going to, in essence, we're multiplying 1 to this 1 over cube root of 3. So notice if we're going to multiply these fractions, recall our lesson in multiplying fractions, that is multiply numerator to numerator, denominator to denominator. If we do that, 1 times square root of 3 is just simply 1 square root of 3. It's actually okay not to write the 1 anymore. Okay, but let's just do that there. So square root of 3 times square root of 3. It's like saying square root of 3 squared. So by one law of the radicals, what we have is cube root, or rather square root of 3 squared is gonna give us, or gonna leave us with 3. But in the denominator, what we have is, or in the numerator, what we have is the cube root of 3 since we multiplied that by 1. So our answer is the cube root of 3 over 3. Or if you want, it may be written as 1/3 times square root of 3. Okay, any of these answers will do. They're equal actually. Okay, so square root of 3 over 3 or 1/3 square root of 3. 1/3 times square root of 3. For the next example, for number 4 still, we have the cube root of 2 over 5. So let's distribute by one law of the radicals. We have cube root of 2 and we have cube root of 5. We're going to do rationalization in this part. So if we rationalize, we're going to multiply it in such a way that we will make sure that the denominator is going to be equal to 1. So what we're going to do is to combine this with a cube root of 5, but not only 5, but it's going to be 5 squared. Okay, the cube root of 5 squared. Likewise, we're going to, if whatever we want or our choice is in the denominator, we're just going to follow that with the numerator, since our main goal here is to delete the denominator here. Okay, so how do we particularly choose our term that we will use for the rationalization? It's going to make it's going to be in such a way that the denominator, we will get rid of the radical sign of the denominator. Notice that the denominator have a cube root of 5. So imagine a cube root of 5 in a fraction form will be something like 5 raised to 1/3. So we need to make this 1/3 become 1. How can we make that become 1? By multiplying this to 2/3, right? Or by adding, rather, by adding that to 2/3. Okay? Or yeah, by adding that to 2/3. So if we're going to add 2/3, if you're going to add that with 2/3, that's going to give us 3 over 3, which is equal to 1. And that's what we want to do to get rid of the square root symbol. So this becomes cube root of 2 times the cube root of 5 squared. Okay, what is 5 squared? 5 squared is 25. And we have a cube root of 5 um, within cube root of 5 cubed. Why do we have 5 cubed? Because we have a 5 here which is raised to 1 and a 5 here which is raised to 2. So we can combine them since they have the same index. So what we have here, since in the numerator they also have the same index, we can combine them actually. So 2 times 25, 2 times 25 is going to give us 50. So that's the cube root of 50. And then in the denominator, we can see that the cube root of 5 cubed is going to give us 5. That is getting rid of the whole radical. That's what we want to do here actually. We can just simplify now, and in the numerator, the cube root of 50, we may think of one number which is a factor of 50 in which it is a perfect cube. And if you're just going to give it some time, you will notice that there's none. So therefore, this is our answer. This can be our answer. Or if you want to extract the 1/5, this can be equal to 1/5 times the cube root of 50. Okay, so either of these answers will do actually. Okay, and we're here in the last principle in simplifying radicals. For the last principle, we say that there should be the one that I've been talking about a while ago, there should be no radical sign in the denominator. So notice here in our first example, we have 10 all over square root of 2. So very clear that there's a radical sign over here. So what will we do? We will rationalize by multiplying this by 2 here, multiplying this also by 2 here, or rather 2, sorry. This will become 10 square root of 2 by multiplying numerator to numerator, denominator to denominator. Square root of 2 in the denominator, square root of 2 will be squared since there's 2 of them there and they're being multiplied. So square root of 2 squared is going to give us just 2. Okay, and we can see that we can cancel up the coefficients. So 10 divided by 2 is going to give us 5. Okay, that's going to give us 5. And we have 5 square root of 2. And this is our answer for the letter A. 5 square root of 2. For letter B, we need to get rid of this 3 cubed, or rather, sorry, cube root of 3. So we're going to multiply. Similarly with the one above, we need to multiply that by the cube root of 3 squared. So the cube root of 3 squared. So if I'll do that, what do we have? Um, for the numerator, we have 12 times the cube root of 3 squared. 3 squared we know as 9. And we have the cube root of 3 raised to 3 in the denominator. Since we have 3 raised to 1 here and 3 squared, so we have 3 raised to 3. Simplifying that things, what we'll have is 12 cube root of 9 all over 3. So we can cancel this up. So this becomes 4 cube root of 9. And that's our answer for the number 5. Okay, so that's it for this video in the principles of simplifying radicals or radical expressions. We will be having more in the future video. And yes, thank you very much for watching. Hope you would like and also subscribe. Okay, see ya.